orthogonality and normalization. Now, orthogonality looks like a big word. Actually, it just means that two vectors that are perpendicular to each other. That's all we mean by it. That is, if a vector like this one makes 90 degrees in two dimensions, so those two vectors are orthogonal, and their dot product will be 0. For example, if you have, let's say, a vector 1 and 2, and then another vector, let's say, -2 and 1, let's say, their dot product, their multiplication will give you -2 plus 2 gives you a 0. So 1 and 2 and -2 and 1 are perpendicular or orthogonal to each other. Okay. So if two vectors are perpendicular to each other, we call them orthogonal. Now, in vibrating systems, we have something more than this. We have the mode shapes of vibrating systems are orthogonal with respect to mass and stiffness matrices. Now, what does this mean? This looks like complicated. It means the following. If you have two eigenvectors, two mode shapes of a system, Ui and Uj, if you put the mass matrix in between them and multiply them, Ui transpose and Uj, you are going to get 0 if I and j are different. If I and j are the same, you won't get 0. But if they are different, you have different mode shapes, they are orthogonal with respect to the mass matrix, which means that this multiplication will always give you 0. And the same is true for if you put the stiffness matrix in between. Okay? The mode shapes satisfy this property all the time. Another thing is the normalization. This is orthogonality. When we talk about normalization, we try to find a certain constant for our vectors so that their length is normalized. Okay, if you have a vector u, let's say, its length is, if you might know this, or u transpose u is the square of the length, and if you take the square root of that, that gives you the length of a vector. Okay. Now we want to normalize our vectors so that their length is, sometimes we want to normalize that their length is 1. How would we do that? We know that the eigenvectors or mode shapes have a free factor, like if u is a vector, alpha times u is another mode shape or another eigenvector. So we select that alpha so that the length of our vector becomes 1. Actually, it looks complicated, but it is not. For example, if you have a vector 1 and 2, its length squared is 5, isn't it? Because 1, 2 times 1, 2, as you know, 1, 2 multiplied by 1, 2 gives you 5. Which means that the length square of your vector is 5. So if you divide your vector by 1 over root 5, the length of your vector is going to be 1. Indeed, the length of the normalized vector, if you divide it by 1 over root 5, this root 5 and root 5 gives you a 5, and this 1 and 2 multiplied together gives you another 5. 5 over 5 is 1. So now this un is the normalized version of your vector, okay, or the eigenvector. So you normalize it by finding its length squared and taking it, dividing it to the square root of that length squared. Okay, that's how you normalize a vector. Now this was regular normalization, but we also have the so-called mass normalization. Mass normalization is an important step in the modal analysis of vibrations. We will see why that is the case later on. What we do is the following. Let's say that we have this triple product, UI transpose and UI. And we know that if you have UI and UJ there, it would be zero for vibrational systems. I will prove that to you. But if you have UIs on both sides, you will get a certain number, like gamma. We will normalize our U's, our mode shapes, so that our gamma will be equal to 1. If that is the case, then our eigenvector or mode shape is going to be called mass normalized. Again, we have a factor alpha times ui, let's say, okay? Now you can show that if you select this alpha I as ui transpose MUI and take the square root of that and take the inverse of that, or 1 over that, in that case, the normalized vector is going to be, you have two alphas here, alpha goes out, so you will have this thing divided by this thing, so you will get a 1. So if you divide your mass matrix indeed by the following, if you divide your eigenvector by the following factor, alpha I equals 1 over root ui transpose MUI. If you do that, then you will be mass normalizing your mode shape or the eigenvector. Okay, this is an interesting result. For example, if you have, this is just an example, if you have a u is equal to 1, 2, 3, let's say, 1, 2, 3 is your mode shape, not normalized, and your mass matrix happens to be 2, 1, 2 in the diagonals. Now, if you do this triple product, U transpose MU, it's a little bit involved, but not much. You can do it even by hand. You will eventually get 24 out of this thing. And if you divide this, your original matrix by 1 over root 24, then your mode shape is going to be mass normalized. Because now if you take U transpose MU from this thing, you are going to get a 1. So here, the U transpose MU will give you 1. U transpose U will be 1. If you have it mass normalized. Now, one interesting property of this is the following. You had an eigenvalue problem, remember. K minus omega squared, that means times ui. If you multiply it by ui transpose from the left, you will get, if you open it up, ui transpose k ui, okay, this is the triple product with k, and also ui transpose MUI. But we know that this ui transpose MUI was 1 if you mass normalize your equations. So what are we left with? This is 1. So ui transpose KUI will be equal to omega I squared, which is the I natural frequency squared. So if the ui is mass normalized, ui transpose KUI is omega I squared. Okay, this is one result. If you do things correctly, this is what you should get. Okay, this will be a scalar, and this scalar will be natural frequency squared. Moreover, we said that the modes are orthogonal. Mode shapes are orthogonal. What do we mean by that? We meant that the triple product of ui, for example, uj transpose MUI or ui transpose MUJ, if I is not equal to j, should be 0. And here we have a mathematical proof of that. What do? We take the eigenvalue problem again. K minus omega I squared MUI equals 0. You multiply it with another eigenvector, not the same one, but another one. Okay? So this is equal to 0. You open it up, Uj transpose KUI. Now J and I are not the same. Times omega I squared Uj transpose MUI. And you take the eigenvalue problem with the jth eigenvector and multiply it with ui now. You get another opening, okay, like this one. Now, the ones I am circling here, this is a scalar and this is a scalar. And look at that, they are the same. These scalars are just the same matrices multiplied in one order, the other one is multiplied in the other order. So they are the same, they are equal. So are these, okay, they are the same matrix. So if you subtract them from each other, these are going to cancel each other, and we are going to be left with omega I squared minus omega j squared Uj transpose MUI equals 0, okay? Since the natural frequencies are not equal, this part is not equal, then this part has to be 0. And this is what we wanted to prove. We said that the mode shapes are orthogonal with respect to the mass matrix, okay? This is what we had claimed, and we have proved it actually. And if we have proved this, if you substitute it here, this is 0, then you find that ui transpose kuj is also 0. So we have proved that mode shapes of vibrating systems are orthogonal with respect to mass and stiffness matrices. That is, if you take mass and stiffness matrices of two vibrating systems, and if you find the eigenvalues of those systems, you will find that these eigenvectors or these mode shapes satisfy the following property. And if you mass normalize them, they will also satisfy. This is. Ui transpose MUI equals 1, this will be mass normalized. If they are not mass normalized, they won't satisfy this equality of 1. They will just give you some number, but they won't be mass normalized. Now, this is an important property. Well, first of all, we will be using this property, the property of orthogonality of the modes. But mass normalization, although it is not essential, you can live without mass normalization of the mode shapes, but it gives you much cleaner, much nicer results in the modal analysis if you mass normalize your mode shapes. Secondly, in these examples I gave you, in this example where you have masses are the same, you don't have to really mass normalize your eigenvectors. The eigenvectors themselves are orthogonal with respect to each other. You don't have to mass normalize them. For example, if you take the dot product of these two eigenvectors, they will give you 0. Each of them will give you 0. So if the masses are the same, you don't have to mass normalize. But if you mass normalize it for a system with different masses, you will get nicer results. Okay. So let me